Welcome to Algotech Programming Concept. In this video lecture, I am going to discuss height balance binary search tree, that is AVL tree, where balance factor is computed for each node, and balance factor is computed height of left subtree minus height of right subtree. So question arises, if we have already binary search tree to store the keys, then what is need of AVL tree? If you see, this is right skew binary search tree, and if you want to find node y, or if you want to find key y, so you will start search of node y from root node towards right subtree, and at last level you will find y. So here the time complexity is order of n, where n is the number of keys, and here number of keys are 5. So this is the worst case time complexity of binary search tree. And we can store these 5 keys in order of log n base 2, means we can store these 5 keys in less height, and we can improve the time complexity of binary search tree from order of n into order of log n base 2. So that is the purpose of AVL tree, and we can convert this right skew binary search tree into balanced search tree by applying some rotations or by applying the color scheme also. So AVL tree is strictly height balanced tree, but red black tree is not completely height balanced tree. So in AVL tree, searching, deletion, insertion, minimum and maximum element, we can search faster. So the tree is unbalanced in 4 situations in AVL tree. So these are the 4 cases where tree is unbalanced. So first case is that left. Here for each node we have to compute balance factor, and this is the first case. This is the first case, left case, means this node C is left of its parent H, and node A is left of its parent C, means A is child of C and C is child of H. So you can see here balance factor is +2. When balance factor will be +2 or balance factor will be -2, then we have to perform the rotations to balance the tree. So this is the first case where left case. So here the balance factor, you can see at node H, the balance factor is positive 2. So we have to perform right rotation. For positive numbers we have to perform right rotation, and for negative number we have to perform left rotation. And this is the second case, right case. Here we can see that V is child of U and W is child of V. So this is the right case. Here again we have computed balance factor. So here balance factor for node U is -2. So this is -2. So we have to perform left rotation. So for minus negative number we have to perform left rotation here. Case 3 is left right case. You can see that here 69 is left child of 88 and 75 is the right child of 69. So this is the left right case where tree unbalanced. Here we have to compute balance factor. So you can see that balance factor for node 88 is +2. But in left right case, first we have to perform left rotation for mid node, and then we have to perform right rotation for node number 88, where +2 comes here. Then fourth case is right left case, where we can see that node X is right child of node V and node W is left child of node X. Here we again computed the balance factor. So node, this tree is unbalanced, and we have to perform right rotation first on node X, and then we have to perform left rotation at node Y. So we have to learn that what happens in rotation, in left rotation and right rotation, what happens. So we will see in the next slide. So this is the first case, LL case, left case. Suppose we have 3 keys here, H, C and A. So we have inserted first H, so balance factor is 0. Then we have inserted node C. So this is a binary search tree where the node C has a smaller value than node H, so it will come in the left side. We again computed balance factor, height of left subtree minus height of right subtree. So the balance factor of H is 1. So in AVL tree for 0, 1 and minus 1, we understand that tree is balanced. When the balance factor will be positive 2 or negative 2, then tree will be unbalanced and we have to rebalance the tree. And when we insert key A, then we again computed balance factor. Here for node H, balance factor is 2. So this is positive 2, so we have to perform right rotation. So in right rotation, the node H will become right side, will be placed at the right side of its left child. So the left child of node H is C, and we have to put this node H on the right side of this node C. So definition of right rotation is that the node H will be placed at right side of its left child C. So node H will be placed on the right side of its left child C. So node H is placed on the right side of its left child C as it was in previous stage. So now we again computed the balance factor. Here tree is balanced. So this is our right rotation, means LL case, left case, when the tree unbalances in the left for the left factor. And in the next slide we will perform left rotation, means RR case, right case. Here we have three keys U, V and W. So again AVL tree is binary search tree. So insertion will be done like as binary search tree. So node U, then node V, and then we have inserted node W. Again we have computed balance factor for node U. We can see here the balance factor is -2, means tree is unbalanced. And for negative side, if we have -2 value for any node, then we have to perform left rotation on that particular node. So that definition of left node is that node will place at the left side of its right child. So what is the right child of node U? The right child of node U is V. So U will be placed at the left side of its right child. So you can see definition here. In left rotation, node will be placed at left side of its right child. So the V is the right child of node U, and U will be placed at the left side of V. So this is the means we are rebalancing the tree, and this is our balanced tree after performing the left rotation. And third case is left right rotation. Okay, so tree is unbalanced due to left right rotation. Okay, so we have computed the balance factor here. So in left right rotation, we have to first perform left rotation, then we have to perform right rotation. So we have to perform left rotation at mid node. So what is left rotation? This node 69 will be placed at the left side of 75. Okay, and the connection will be break here. Okay, so again means 88 will be parent of this node number 75. So this is our left rotation. Then we will perform right rotation on node 88. So and definition of right rotation is that this node 88 becomes the right child of its left child. So left child is 75, and 88 will be placed at the right side of node 75. So in this scenario we are getting balanced tree. And the fourth case is due to right left rotation, the tree is unbalanced. This is our right left rotation. If we insert the keys in this fashion, so we will get unbalanced tree and we have to rebalance it. So here the balance factor for node V is -2, but this tree is unbalanced due to right left rotation. So we have to perform first right rotation for mid node. After that we will perform left rotation for node V. So we will perform right rotation for mid node X. So X will become right child of W. Okay, and again the node V will be parent of this node W. So there will be pointer disconnection, and again we will join the childs with the help of pointers here. So this is the right rotation. and we can see that for node V the balance factor is -2. So -2 means we have to perform left rotation at node V. So the node V becomes left child of its right child W. So node V becomes left child of its right child W. So V is placed in the left side here. But one main thing you have to see here, that in order keys, here you can find in order is V, W and X, and after performing the rotation we are getting the same in order keys. Okay, so remember it, whatever the in order in the starting, you will get same in order keys after performing the rotation for all the cases, whether it is LL, RR, LR and RL. So you will get in order keys, you will get same in order keys. Okay, now we are doing exercise, and we have to perform AVL tree on this UVWXYG. So in the starting first slide you have seen the right skew binary tree. If we make the right skew, we make insertion for these keys in binary search tree, so we will get height is equal to 5. So that will be right skew binary tree. But we will perform, we can store these keys in AVL tree in order of log n base 2, means at height is equal to 2 we can store all these keys where searching, insertion, deletion, minimum, maximum element we can found faster. So and we are going to start the insertion of these keys for AVL tree. So node U comes, we have computed balance factor, height of left subtree minus height of right subtree, that is 0. Then we have inserted node number V, so V is greater than U, so V comes in the right side. Here we have computed balance factor. For node U the balance factor will be height of left subtree, that is 0, minus height of right subtree, that is -1. Then again we have inserted node W. When we inserted node W, then you can see that for node U the balance factor is -2, means -2. So it is, this tree is unbalanced. For -2 means we have to perform left rotation for node U. So U becomes left child of its right child V. So you can see here U becomes left child of node V here. So tree is balanced again. Then we have inserted node X. So node X will come right side of W because the key value of X is greater than W. Again we have computed balance factor. So here balance factor is 0, -1. So this tree is balanced. Again we have inserted node Y. When we have inserted node Y, then this tree is unbalanced. And you can see the balance factor is for W is -2 because the left subtree height is 0 and right subtree height for node W is 2. So 0 minus 2 is -2. And again we have computed the balance factor for node V, that is also -2. The height of left subtree is 1 minus height of right subtree is 3. 1 minus 3 is -2. So but we will perform first the operation for node W because we are getting the -2 value for node W first. So we will perform left rotation for node W. So the definition of left rotation is that the node W will become left child of its right child. So node W will be placed left of its right child X. So you can see here that W is placed at the right, at the left side of its node X. So now this is balanced tree. So like this we have seen that there are 6 keys and we can store these 6 keys in order of log n base 2 times. So here we can compute the height is 2, so our the operations will be faster. And if we store these keys in right skew binary tree fashion, then the height will be 5. So this is the advantage of AVL tree. So in the next video we will discuss some more example, and we will discuss some special kinds of rotations. Suppose if we want to perform the right rotation on this node 38 is carrying one right subtree also. So this kind of rotations, these are the special kinds of rotations. So please watch my next video to find the answer. And there are 4 to 5 special kinds of rotations are there for these types of questions. So please watch my next video.